Hi Math 10s, it's Mr. Johnson here. I wanted to do a little video to help you out so that way we could maximize our class time. The purpose of this video is for me to do my lecture that might typically take 30, maybe even 40 minutes in class to go over while we spend time either copying notes or asking small little questions here and there, and put it online so that you can pause, so that you can copy without missing anything, and even rewind the lecture. So I hope this helps you out, and this will allow us to use our entire class time on focusing on you, practicing, asking any question you really want to. It can be a discussion if you want, or it could be just an individual question on something you have a problem with. But I think this will help maximize our class time and focus on some of the questions you may or may not get stuck on for homework. So our topic of the day, systems of equations. We're expanding our knowledge on linear equations. Our learning target is that I can set up a linear system of equations when given context. That means the information to the question. First off, what is a system of equations? That's whenever you have more than one equation with more than one unknown. Last unit, we had one equation. We had one piece of data that we did not know. We had to solve for it. Two ways to solve for it: graph it or use algebra. Those are your two ways. Problem solve through it. This case here, it's very similar techniques. You could solve by graphing. You can solve by some other algebra methods that we'll get into later on in this chapter. But for right now, what's a system? Well, an example of a system of equations would be like this. This here we have two equations. We have 2a plus 3b equals 12, and then a second equation, 6a minus b equals 2. We have two separate equations, and we have two unknowns, the a's and the b's. Having two unknowns, you actually need two equations with those unknowns in order to solve it. It's kind of like you're a detective. So last unit, we had one equation, one unknown. This unit, two equations, two unknowns, as well as three equations, three unknowns with the x, y, and z. Once you understand the steps on how to do a two-equation question, the process is extremely similar to a three-equation question. And we call them essentially a system because they go together. The information is linked. So where do we see this? Well, let's take a look. Consider a school district has vans that carry 12 passengers and buses that carry 24 passengers. The total passenger capacity is 780, and there are 20 more vans than buses. Write equations to represent this system. Well, if you trust Ned Stark over here, he'll tell you that one does not simply forget to define the variables. In order for us to make sense mathematically of what's going on, we need to talk about and define what is being discussed here. So we're talking about two key things: vans and buses. Okay? So what we need to say to define those, let V equal vans and B equal buses. Very similar to what we did in our past unit with linear relationships. Now, let's get the equations. So this is where we're going to notice the words. We have vans carry 12 passengers and buses carry 24 passengers. So that's like 12V and 24B. And the total passenger capacity is, mathematically, we know that means an equal sign, 780. So that would be one equation. Okay, but where we have a system, we have to deal with two or more equations. And that comes from the second piece of information here. It says that there are 20 more vans than buses. 20 more vans than buses. So if we wanted to make that equal, we could say that buses plus 20 will equal the vans, or vans subtract 20 will equal the amount of buses. So those are the two equations that you could use. Only difference is here that I guess I moved the 20 to the other side. I subtracted that to get b alone by itself. So I could get either b plus 20 equals v, or v subtract 20 equals b. Either or, you're still going to get the same answer. But pay attention to the words of the question, and you want to make sure that it says it's equal to. Okay. Consider the following, same question here. B, so it says verify that there are 35 vans and 15 buses. Similar to our past unit, when we talked about verifying, that means that we're checking our answers. I'm not going to show you how to get to the answers here right now. We're going to have to discover that on our own later. But we just want to check and make sure that our equations are right. If we are able to verify with a solution, the left-hand side of the equation should equal the right-hand side of the equation. So if I take a look, I'm going to use my first equation, 12v plus 24b equals 780, and I'm going to substitute my 35 in for vans and my 15 in for buses. And then I'm going to do my order of operations. 12 times 35, that's 420. 24 multiplied by 15 is 360. Add the left-hand side up of this equation. So 780 equals 780. So that's good. And I have to verify with both equations. In order for this to be true, it has to work for both equations. So let's take the b plus 20 equals v. You could use the other example that I mentioned on the last slide. And you're going to substitute the 15 in for the buses and the 35 in for the vans. And if the left-hand side equals the right-hand side, that means that both equations are true. And if both equations are true, then they are verified. Okay? We're verifying. We're checking our math. So here's a check your understanding question from your book. Create a linear system to model this situation. The stage at an outdoor concert is rectangular. Its perimeter is 158 feet. The width is 31 feet less than the length. So notice that second statement there. It's probably a second equation. Well, this case where it does mention that the shape is rectangular, that's really going to be helpful perhaps if you, let's say, draw a diagram. So you know with a rectangle, you have two longer sides, which are defined as your lengths, and then you have two shorter sides, which are your widths. And so just recalling our perimeter formula, we would know that your perimeter is 2 lengths plus 2w. And we can't forget, we have to define those variables. Let L equal length, let W equal width. And you could even specify here, you could say in feet, length in feet, width in feet. Okay, and our second equation, so that's going to be 2 length plus 2 width equals 158. And now our second equation has to do with, it says the width is 31 feet less than the length. So how do you make that equal? Well, you could take the width and you could add 31 to make it equal to the length, or you could take the length, subtract 31. Okay, it is up to you. Okay, if you don't want to use these, like you don't want to have three equations here. So for our equations, this would be equation number 1, and this would be equation number 2. If you don't want to use this here as the equation number 2, you could definitely use width equals length, subtract 31. and that would be okay. Okay, once again, so Sebi has determined that the stage is 55 feet long and 24 feet wide. Use the system from part A to verify. So what you're doing is you're substituting in 55 for your length, 24 in for your width. And we have to verify. Does this right-hand side equal our left-hand side? Yes. And likewise with the second equation. If they do, that means both things are true, and you've now verified yourself. Checked your math. Good job. Okay, let's take a look at the second check your understanding example. Create a linear system to model the situation. A school raised $140 by collecting 2,000 cans and glass bottles for recycling. The school received 5 cents for each can and 10 cents for each bottle. If you want to try this question on your own, you're more than welcome. Pause here, and then we'll continue on. Okay, so now, first things first, let's define those variables. Let B equal bottles. You could even say glass bottles. Let C equal cans. For our first equation, okay, so we have what? We got the $140. We have 2,000 cans. We have another money thing here. We have 5 cents for a can, and then we have 10 cents for a bottle. So if you notice, money kind of goes with money, and what's remaining can be another equation. So if we look at this, we have 2,000 items that are collected, 2,000 cans and glass bottles. So B plus C equals 2,000. And then, if we want to talk about the cent value, 0.05 C plus 0.10 B equals 140. 5 cents a can, 10 cents a bottle. Those are going to be your two equations. Okay, now it tells you the school collected 1,200 cans and 800 bottles. Use the system from part A to verify. If you want to pause the video here, go right ahead. Okay, so now what we're going to do is we're going to use our first equation, which was B plus C equaled 2,000. Our bottles, which was 800. Okay, so we got the 800 bottles, and we have 1,200 cans. Added those up on the left-hand side. 800 plus 1,200 is 2,000. That checks out. That's good. Okay, now our other equation, which is a little bit lengthier. So we have our equation that we found out, and we're substituting that 1,200 in for the cans, the 800 in for the bottles, and now we're just multiplying. So we have 0.05 multiplied by 1,200, which is 60. 10th multiplied by 800 is 80. And then $60 plus $80 is $140. Okay, so that checks out as well. So that means that everything is true. So hopefully that helps you out on being able to set up the systems of equation when you're given the context. Now what we're going to do in class, we're going to focus on word problems where you're going to examine the context of the question and then create systems of equations.